In this video, we're going to look at how to read and interpret carbon-13 NMR spectrographs. This is part of our requirements for Achievement Standard 91188, Level 3 NCEA on spectroscopy, the spectroscopy internal standard. If you find this video helpful, don't forget to share, like, and subscribe, and look out for new videos. Interesting thing about carbon is that carbon-13 isotope has something called a spin quantum. The carbon-12 doesn't. Now, spin quantum means that the actual nucleus inside a carbon-13 will spin or rotate, and as it does this, it will produce a magnetic field. A carbon-12 nucleus doesn't, but so because of these carbon-13 nuclei, which is about 1% of the carbon sample, we can produce spinning nuclei that produce their own magnetic field. Now, if we take these nuclei that produce their own magnetic field and we place them in an external magnetic field, they're going to do one of two things. As the magnetic field spins, they're either going to align themselves with the magnetic field, okay, so they're spinning with the magnetic field, or they're going to align themselves perfectly against the magnetic field. If they align themselves with the magnetic field, as in the green nuclei does here, it's said to have a lower energy state. And if it aligns itself against the magnetic field, it's said to have a higher energy state. Now, what we actually do is if we just bombard these nuclei with an energy source, with a high frequency energy source, and then they're all going to start spinning, right? So, and they will produce their own magnetic fields. And then we put this magnetic field, we put the magnetic field on, and they get caught. Now, these nuclei that are in the high magnetic field are going to, after a time, will all want to go back down to the lower energy state. They're in a high energy state, and as they fall back down, they're going to do a special thing. So remember, we have this we can have this carbon-13 nuclei that's spinning against the magnetic field, and it's caught in a high excited energy state, we call it. Now, what happens is it's going to, at some stage, fall out of that excited energy state and fall back down to the stable state. As it does this, there is a difference in energy between these two states, and the energy that it had when it was at the top compared to the bottom is released as a burst of electromagnetic energy. And that burst of electromagnetic energy is detected, and then from that detection, we can determine exactly what frequency the light energy is at. So it gives off a burst of light energy, and we detect the frequency of this light energy. We then plot this on a graph, and this is a carbon-13 NMR graph. Now, it so happens that the height of this excited energy state is actually influenced by what other atoms are attached to the carbon atom. So if we have atoms like oxygens or maybe chlorines attached to a carbon atom, it will increase the size of this energy state. So we will get different amount of energy coming off. So let's have a look at the carbon-13 NMR graph on the next slide. Okay, so here is a picture of a carbon NMR graph, a carbon-13 NMR graph. We have this scale along the bottom that's called parts per million. Don't worry about what that means. It's to do with how much energy is given back after we send energy at it. Don't worry either about the height of these lines. The height of these lines don't actually tell us anything about the abundance of the carbon. It's just each one of the lines actually refers to a separate carbon environment. Now, you heard me right. I talked about not a separate carbon, but a separate carbon environment. We'll see if we can unpack that idea. So here is a molecule here. This is propane-1-ol. You can see here that there are 1, 2, 3 carbon atoms. 1, 2, 3 carbon atoms. But each of these carbon atoms is bonded actually to 4 different substituents. Now, I'll show you what I mean by this. So This first one here, which is, I'm going to call this carbon 3, it's bonded to a hydrogen, another hydrogen and a third hydrogen, and then it's bonded to a CH2, CH3, so it's got this whole substituent group here that it's bonded to, and it's also bonded to these 3 hydrogens. Now if we were to take carbon 2, and here's carbon 2, it's actually only bonded to 2 hydrogens, a CH3 group on the left and a CH2OH group on the right. So it is a different environment than the one on the left. And if I go to the one on the right, it's actually bonded to an OH directly, a CH2, CH3 on the left, and 2 hydrogens. Now each one of those carbons is in a unique environment or bonded to different substituents. So they have different unique peaks on the graph. Interesting to note as well that what happens when you're bonded to an oxygen is it pulls you further along to the left on this plotted graph, further higher up the plotted graph. And notice here that I can detect that the first carbon here is the one closest to the oxygen, and the second is the next closest, and then the third is the furthest away. Okay, so here's 2 more examples. Now let's have a look at this one here. So if you look at the one on the left here, you can see that there are 2 distinct peaks. You can also see from the molecule that means that there are 2 carbon environments, okay? 2 unique carbon environments, and if we look that it came from this molecule on the top, we can see how this came about. So there is 1 carbon environment, that is the carbon that's attached to the chlorine, and you know what, that's going to be the one shifted the most because the chlorine pulls it a wee bit to the left. And then we're going to have the 2 carbons, the one on the left and the one on the right, are both attached to the same groups, 3 hydrogens and a C2H4Cl group for both of them. That's what it's attached to. If I look on the one on the right, this molecule, so it's very similar. So this is 2 chloropropane and this is 1 chloropropane. We can see that there are on the right 3 distinct peaks. So there are now 3 different carbon environments. Now this is important when we have to write up our report here. We don't just say that there are 3 different carbon environments. We say because there are 3 distinct peaks, there are 3 different carbon environments. And if we generally know that a chlorine shifts our peak to the left a little bit, we can say that this carbon here must be, the yellow carbon must be the peak on the left, the green one, the one in the middle, and the blue one, the one on the right. But notice how each of these is unique, okay? So this carbon, the yellow one has a chlorine and 2 hydrogens, the green one has 2 hydrogens and attached to a CH3 and a CH2Cl, and the one on the left is 3 hydrogens. So we have 3 different environments. Now this becomes a very important technique for starting to pick apart and work out exactly how the carbons are arranged in a molecule and where the functional groups are placed. Notice it will be symmetrical molecules that have less peaks than we might expect. Okay, so if we have a carbon-oxygen bond, that is a carbon that is bonded to an oxygen, either to an OH group or possibly to an ester group, what's going to happen is that peak is going to get shifted into a certain range. It's going to be shifted into 50 to 80 ppm. So because this peak is found between 50 to 80, it indicates it's probably going to be a carbon that is attached to an OH. If we have a double bond, then we're going to have a different shift range. A double bond also shifts the peaks, but it shifts it considerably more to the left. So a double bond will have the peaks between 100 and 150. Notice here, because we have a double bond, there are going to be 2 carbon peaks, 1 peak for each of the carbons of the double bond. And notice that each of the carbons on the double bond are unique, so they're going to have their own unique peak. Okay, so this is interesting, this one here. This is hex 3ene. Now hex 3ene is a symmetrical molecule. It's symmetrical down the middle. So the two carbons that are part of the double bond actually are in the same environment. So they're going to be have their peak at the same place. It's still going to be within the range that we talked about, but there will only be one peak within that range. Notice also, because it's symmetrical, we've only got two other carbon peaks because we have two other sets of carbons that are identical. Notice the carbon-hydrogen bonds, that's the carbons that only have carbon-carbon and carbon-hydrogen bonds, are found within the range 60 to 0. And if they're not directly attached to a chlorine or an oxygen, they're usually found lower down the range. Okay, so a carbonyl group is the one that gets shifted the most. And remember, a carbonyl is when a carbon is double bonded to an oxygen. Now, carbon double bonded to an oxygen will have a range from 150 to 220. So we can see that this is carbon number 2. Notice here this molecule is also symmetrical, so the two carbons on the left and the right are in an identical environment, so we're only going to have one other peak, and it's in the carbon to carbon, carbon to hydrogen range, that 0 to 60 range. Here's another carbonyl shift here. What I want to notice here is that this carbon actually has a carbon to oxygen, a carbon to double bond oxygen bond, but a carbon to oxygen bond as well. But when we have two competing shifts or pulls towards the left, we actually only take the one that is the largest. So in this case, the carbon to double bond oxygen is going to be the one that we're going to use to locate the peak, and it's going to be between that 150 to 220. We will not have a separate peak for the carbon to oxygen because we have already accounted for this carbon. This carbon is accounted for when I draw this peak, so I don't need to draw another peak at the carbon to oxygen. Okay, so we just ignore the carbon to oxygen. Now we draw the other two we identify the other two carbons that will be down in the carbon to hydrogen or carbon to carbon range. Take care with this. This is a common mistake, is that people will often look for a carbon to oxygen peak, but remember, it won't be there because it's already been accounted for in this carbon to double bond oxygen peak on the left here. So what are the key points of this carbon 13 NMR? Well, the frequency of the energy that's been emitted depends on the other atoms that the carbon is bonded to. That is its unique environment. So any carbon that has its own unique combination of groups atoms bonded to it will have its own specific proton frequency or its own ppm. They are plotted on a graph as ppm. There are the 4 common ranges that we need to remember or comfortable at using if we're given a table of these to pull apart graphs. Okay, so the 4 common ranges that we need to be aware of are the carbon to hydrogen or carbon to carbon range between 8 to 60. Remember, if they're bonded to a chlorine, they're going to be shifted a bit further along. We have if its carbon is joined to an oxygen, whether it's an alcohol oxygen or an ester oxygen, it's going to be between 50 to 80. Now sometimes this range, because it overlaps with the carbon, hydrogen, we have to use other evidence to be definitive about this. However, we can be definitive about the carbon to double bond carbon range, 100 to 150. If we've got a peak in there, we've got a double bond. Remember, however, if it's a symmetrical alkene, we're going to only have one peak because it's only going to be one unique carbon double bond carbon environment. And if we have this peak between 165 to 220, we are going to have a carbonyl group, a carbon double bond oxygen. Okay, hopefully this has helped unpack how you use a carbon 13 NMR graph, and you can use this along with other evidence to identify unknown organic molecules in your spectroscopy.
Okay, if you've got to this part of the video, you've obviously watched all the examples that I had on those 3 questions. Hopefully this has fortified your understanding of geometric isomers, and you are now well prepared to go and attack that exam. Good luck, and if you found this video useful, don't forget to like it, subscribe, and look out for new videos that I might put up by clicking that bell. See you later.